Australia is facing an increasing epidemic of type 2 diabetes. There are now approximately 1 million people living with diabetes and around 100,000 new diagnoses each year. Obesity is thought to be the primary cause of type 2 diabetes in people who are genetically predisposed. In part 1, we explained how inflammation in type 2 diabetes destroys the pancreas tissue and dramatically decreases insulin production. Here we describe the insulin receptor in type 2 diabetes.
What we have discovered is the molecular detail of how the hormone insulin binds to its so-called receptor protein on the surface of a cell and instructs that cell to take up glucose from the blood and to store it as an energy source. The receptor itself actually spans the cell membrane, so it has a part outside, a part inside, and insulin binds to the part that is outside. Insulin is a small molecule whose structure was determined a long time ago in 1969, but it's been unknown how it interacts with the receptor, and that is what we have discovered. And its interaction I've characterized as a molecular handshake as the two proteins dock together. When insulin binds to the outside parts of the receptor, it brings the two halves of the receptor together, and at the same time, the two parts inside of the cell unwind and make contact. These two proteins then activate each other.
This activation allows the insulin signal to enter the cell. Specialised proteins interact with the activated receptor just below the cell's surface. The receptor activates these proteins, and they in turn are able to activate multiple other proteins in a long signal cascade. This complex signalling process eventually tells the cell to take up glucose for use as an energy source. The long signal cascade allows tight control of the signalling process, as it can be turned on or off at many different points along the way. In type 2 diabetes, we believe insulin binds to its receptor normally, but the signal is not sent into the cell and the signal cascade does not develop. This is known as insulin resistance. This means that glucose cannot enter the cell and blood glucose remains high. Over time, high glucose levels damage many different organs.
Insulin, as you know, has been used to treat diabetes for a very long time. But all of those formulations and types of insulin that have been used in the diabetes context have been designed and formulated without any knowledge of the way in which insulin actually interacts with the receptor. And now for the first time we've got a picture of that, and we can use that into the design of new insulins that could be used for the treatment of diabetes. So we could imagine, for example, the design of insulins that act for a longer period of time, design of insulins that act more quickly, design of insulins that are more stable upon storage, and that's where we'd like to go with our discovery.